As we push faster and higher toward aerospace superiority, each part of a weapon becomes more specialized. The Air Force calls for an integrated design approach to each weapon system, and so many elements are developed specifically for one air vehicle. However, greater demands on the air crew call for ever closer relationships between man and machine. Instruments, therefore, have been a major exception to the weapon system concept, seldom designed specifically for any one weapon system. Perhaps the most important reason why most instruments are standard Air Force items is training. Imagine the confusion if a pilot faced a completely different panel each time he changed aircraft. Imagine some vital split second while the pilot adjusted himself to some new reaction from an unfamiliar instrument. Under the Air Force Integrated Panel Program, pilots will find generally a new look in instruments, but with a real consistency among aircraft. Pilots need the best balance between the specialized panel, which fits only one model of aircraft, and the rigidly standardized panels, which fit all aircraft but don't really do the job on any of them. They'll find that balance when elements of display and control are integrated with aircraft subsystems under the principles of the whole panel concept. In the design of the panel and flight control subsystem, weapon system contractors will establish procedures to ensure that all aircraft subsystems are linked effectively with panel displays and controls, so the flight crew can carry out the assigned missions in the safest, most effective manner. Imagine a weapon system contractor designing a panel subsystem for a completely new weapon. It could be a manned orbital space bomber. It could be the mobile flight control station of a missile system. It happens to be a fighter bomber. To examine the problem of display and control design of a typical weapon system, we'll visualize a completed aircraft like this, but only for purposes of discussing procedures. We'll look at three major categories of effort and hear from the man who heads each function. Operational analysis. What must the weapon do? Display engineering. What must the crew see and control? Systems integration. How can each subsystem be matched to all other subsystems? Let's begin with operational analysis, for the panel and control design will be governed by the missions, more so now than ever before. Let's hear from the contractor's Mr. Operational Analysis.
I suppose there isn't any specific point where you can say our work in operational analysis begins. In study phases, we work from definitions of general missions and tactics. For this fighter bomber, our operations people are trying to predict the detailed operational conditions, considering many factors, including friendly and enemy electronic ground environments. You are all familiar with mission profiles, showing such factors against altitude-distance relationships. Our effort must be closely coordinated with what we call the Systems Integration Group, which is establishing requirements for guidance and control subsystems.
Our work in systems integration includes the assembly of information on flight control equipment to fit the requirements of the weapon system missions. We have to determine the types of subsystems and from each subsystem the required function output. The selection of types of flight control equipment is an important factor in the crew function studies based on the mission analyses.
In operational analysis, our human factors people examine each mission profile, translating it from a base of miles to a base of minutes. We want to examine crew responsibilities at each minute, a task analysis. In some cases, we will examine the mission second by second, as, for example, the takeoff. Watch how quickly things happen here. Second-by-second analysis of crew responsibilities is required during some flight phases. Longer analysis intervals are used on other phases, where the requirements are essentially constant for longer time periods. We keep alert for phases such as the attack, where perhaps too many things must happen at once. Operational analysis uses every means possible to simulate missions and to perform tests, so we can recommend which functions should be automatic, which functions should be manual, and which ones at the pilot's option should have both automatic and manual control. Such analysis considers many features. Our overall consideration is that the flight crew is superior to machines to carry out operations demanding motor skills, to recognize and interpret complex patterns, and to maintain flexibility of decision. While we work on the crew function study, we supply detailed analyses of the aircraft missions, including three-dimensional mission models, to the systems integration people.
By this time, systems integration has a preliminary schematic drawing of the flight control system. We consider the mission according to subsystem rather than flight phase. This is takeoff flight phase, climb flight phase, followed by cruise, descent for the attack, penetration to the target, and so on. But when we consider the subsystem, which is providing guidance information to displays and to the autopilot, we see that a TACAN system governs this portion of the flight. So the climb and a portion of the cruise would be in a TACAN mode. We see that another portion of the cruise and this descent penetration are another mode, in this case inertial. The whole mission is analyzed this way. In this area, data link controls the recovery and return to base by systems such as VolScan. The final mission phase is approach and landing, perhaps in an ILS mode. So this, combined with timeline operations analysis, gives us a good basis for our study of what the crew must see and do. This determines the signals that must be supplied to display and flight control. We examine how signals can combine for adequate guidance and how the displays can show the output of combined subsystems. From this kind of study, we make up a flight mode analysis chart. We consider each element of display, such as Mach, IAS, safe speed, G, on down through, altitude, heading, course, and so forth. We also examine automatic flight control system references. What is the origin of the signal that will drive each element of display and or furnish a command to the autopilot during each mission phase? From such a chart, we can see, for example, that the bank steer needle might receive inputs from the inertial system through the flight director during the penetration to target. But the same display element should also receive inputs from the terrain clearance system for part of the time. The autopilot may need similar combining of signals from more than one subsystem. We determine all combinations of information sources and how certain signals must be changed or combined for adequate guidance. We can also see the elements of integrated display as they will be used by the air crew. When we complete this chart, it becomes, in effect, the summary of control display needs. At this point, we begin to work even more closely with the display engineering group.
In our display engineering effort, we are studying the nature of the information required by the crew to carry out the specific functions established in the mission analyses. Working with the systems integration people, we study the flight mode analyses to see where existing or developmental displays may not be adequate for use in our weapon system. Display development is in accordance with the whole panel philosophy. Our guide is WADC Tech Report number 56-582. We look for improvements consistent with the state-of-the-art advancement. We recommend new display developments only when they are clearly needed to complete the mission. For example, terrain clearance display is required for the low-level portions of our mission. Perhaps this radar display becomes a part of the flight control system. The pilot may place a pip on the desired flight path so the flight control system can maneuver the aircraft for the best terrain clearance flight. These are things we must study. When we have considered each element of display and flight control in terms of mission function requirements, we prepare a detailed program for development of displays within the time requirements of the overall weapon system development program.
As our systems integration efforts proceed, we use simulation to run a detailed analysis on each subsystem. This tells us whether information from the subsystems is adequate for flight control, and we consider the computer coupler units, which may be used to process or combine signals. We examine each subsystem and each computer coupler unit for these electromechanical characteristics. From this report, we proceed to a detailed system block diagram showing signal inputs and outputs between subsystems and to panel instruments. Here we find problems of interface, where two systems meet. If the output of System A doesn't match the input required by System B, must we add a coupler to match these systems? Or can we reduce the need for couplers by solving some of the interface problems in the design stage?
Display engineering is now ready to undertake our display development program. We work closely with WADC's Flight Control Laboratory under the Air Force whole panel philosophy. Notice that we begin the detailed design of the display and control system only after we know the nature of the information required by the crew. Naturally, instruments that are in existence or in development will be considered first in terms of our aircraft, its mission, and its display requirements. However, we are planning an advanced weapon, and we have to consider instrumentation advances to keep pace with it. Some new displays will be tested by flight crews at breadboard stage, measuring quantitative data in flight control simulation, as in this terrain clearance display. We know that before any display can be installed in a production aircraft, it must be flight tested by the Air Force. As soon as possible, we mock up our first ideas of integrated panels and controls, power plant, fuel management, oxygen, and the rest, as a basis for continued discussion and for visits by the Air Force. We supply a duplicate of this one to WADC, and we keep both mock-ups up to date as developments proceed.
How well have we integrated the systems? We look for ways to eliminate redundant pieces which do not add to flight safety. We check subsystem design requirements in each flight control mode, considering compatibility with electronic ground environments. Now we are ready to design the switching system. We work from the mission analyses and the analysis of flight control modes and signals. You will remember that the flight mode analyses are based on subsystem rather than flight phase. We do not think of this as climb mode, but rather by its subsystem phase, such as TACAN. Now we are reducing to practice the idea that equipment in design stage is modified for systems integration, while modification to equipment in production is by couplers. Constant re-examination of the mission will show the need for interlocks to prevent inconsistent display or control. Suppose the navigation system calls for a right turn to reach the target and the terrain clearance system calls for a left turn to miss the mountain. Need we say more? The layout of the flight control system shows an integrated switching package developed from our system block diagram. In manual mode and each automatic mode, we know what will be computed, displayed, and furnished to the flight control subsystem. We can save time, weight, and cost by the time sharing of certain display elements. The final layout of the flight control system is guided by our switching analysis report.
The climax of all this effort is in the flight simulation facility, with a cockpit which is more detailed and more functional than the usual mock-up, for we want to test much more than how does it look, how does it feel, how does it fit. We'll test these displays and controls in motion, the dynamics of the man-machine relationships. Using our computer facility, we'll simulate each of the missions intended for this weapon. Besides tape recording verbal communications during the mission, we record positions of each control. At this point, we are asking ourselves, how efficiently can the crew operate this system? Can we change anything now to improve this efficiency? We're going to fly this mission in detail, as closely as possible to a real-time basis. We estimate the time for mission planning has already occupied the pilot 1 hour, and the pre-flight inspection 30 minutes. 11:30, takeoff time minus 30, and the pilot is briefed to fly this mission. The aircraft will take off from this base, will climb to altitude, and cruise out. It will descend to the deck before reaching the main line of resistance and stay under predicted radar line of sight. Penetration to the target is high subsonic. After the lab's delivery, escape is on the deck. Climb to most efficient altitude and cruise climb until the recovery system, under data link, controls descent to instrument approach. As we watch this simulation of procedure before starting engines, let's extend our imagination and see how close we can come to visualizing the mission. What are the considerations of this weapon and its missions that affect design of its control and display systems? For example, with this location of air inlet duct, air can be sucked from the cockpit during engine operation. Therefore, the canopy position is internally wired with the starter switch, so the canopy must be down before the engine can be started. We visualize a second-by-second operation, considering each function of each subsystem, each element of display and control which affects the crew. Example, we anticipate that a man on interphone can help ground safety if he hears each step of engine start procedure as read by the pilot from the checklist. We provide a hot mic control so that the pilot can have both hands free for the engine start without pressing a button to talk on interphone. We consider which systems must be checked with engine running and how long it will take to check each one. What can we do with displays and controls that will minimize this time and will get the aircraft into the air with more fuel aboard? Obviously, we must check the functioning of flight control surfaces and hydraulic systems. What do we need besides the usual ground crew pilot intercommunication? Are we providing displays and controls to make this check in the least possible time? Is there a better way than an independent check of each separate system? In the interpretation of fluctuating gauges during transients, How much should we expect of the pilot? Check flight controls, check trim systems, check compass systems. What are the crew functions? What are the best displays and controls? And how long does it take? Ready for taxi. T-minus 8 minutes. What displays need monitoring during taxi? Besides steering the aircraft, what controls must the pilot actuate? Now we're studying the time of each function. The next few minutes are full of busy seconds and critical seconds. Time, T-minus 0. Release brakes, throttle to afterburner. Watch exhaust temperature. Watch nozzle position. Check engine pressure ratio now. And all this time, steer down the runway, first nose wheel steer, then rudder. Lift nose wheel at just the proper speed to fly off in the least ground roll. Consider an instrument takeoff and see how integrated panel action helps pilot. When airspeed marker centers, it indicates proper speed to lift nose to 15 degrees pitch angle for fly-off, shown by climb needle. In the pitch up to climb, angle of attack remains in safe speed range. When we consider the multitude of functions required to fly the aircraft at such times and add to this communication requirements, we may be exceeding human capabilities. Can we provide an integrated tuning system for all radios with memory circuits to reduce the demand on pilots? Should we provide panel displays of frequencies and channels so the pilot does not have to look down into the cockpit at critical times? All right. Level off for initial cruise. Outbound in TACAN mode. The pilot needs cruise control information to achieve optimum range. What parameters should be measured, and what's the best form of display? It's now T+17, and he should be letting down for his penetration on the deck to the target. In our analysis, we assume turbulent conditions at these low altitudes, and we figure that the pilot's shoulder harness must therefore be locked. But let's examine this locked operation. Can we put important controls such as gun and camera switches on the panel? The panel must be 30 inches away for seat ejection clearance, yet normal reach with locked harness is only 28 inches. Should all important controls be mounted on side consoles with linked panel displays? It's questions such as these, with interrelated aspects of operational analysis, display engineering, and systems integration that come out of such flight simulation studies. We try to visualize all the factors which influence each phase of the mission favorably or unfavorably. We consider the inputs that can be derived, computed, and displayed in terms of situation. Look, for example, at a lab's delivery and how it might appear on instruments with a programmed escape maneuver under automatic flight control. And remember, over the target area, things happen mighty fast. In the center attitude director, the horizontal needle commands a 4G pull-up until bomb release. Now, the programmed escape maneuver commanding a quarter roll and a dive out to a new heading. What would night mean to the mission? What about weather? What is required of the aircrew in terms of human capabilities anticipated from test reports and experience? T+60 minutes, and he is cruising home, ready to be picked up by terminal recovery system such as VolScan. Following the principle of analysis by guidance and control systems, we consider the flight control and display functions as the pilot enters the recovery control area and selects the communication channel for data link operation. On integrated display, data link commands a new heading. Here again, we show the pilot where he is, the center airplane symbol, in relation to where he should be. The display provides monitoring information for the pilot as the aircraft is directed through the autopilot to the entry gate for the approach. Throughout the entire process, we conceive of the pilot as the mission manager with airborne judgment and certain human abilities beyond computers and guidance systems. Our mission simulation is carried to the limit of our imagination and our ability to synthesize. Our purpose is to improve design features of displays, controls, and switching systems so the crew will have no difficulties in meeting functional task requirements. Mission completed, and we begin our analysis. We conclude with a report which identifies problems and recommends action to meet requirements. But our job really continues through flight test and delivery of the production articles.
We have visualized three major categories of effort and the many steps of coordinated activity in a suggested development program for a weapon system contractor. What is your development program? The result of an effective program can be flight control and display subsystems, which provide the best balance between standardization and specialization, utilizing the decision-making capabilities of the aircrew and providing for each mission the most effective Air Force vehicles and weapon systems.